Welcome to lecture 23. We're going to continue our discussion on virtual memory. Today we're going to talk about how to reduce the size of page tables using this idea called hierarchical page tables. Before we get into hierarchical page tables, I want to talk about the physical memory and virtual memory configuration on my computer, and I would encourage you to do the same by looking into your configuration of your computer. In my system, I have about 16 gigabytes of physical memory, and I also have some of my disk allocated for storing spilled over data, that is 13.5 gigabytes. So 16 plus 13.5 plus a few other parts of my memory constitute about 29.5 gigabytes allocated for storing data of programs that are running on my system. In Windows, they're talking about it as a virtual memory, but we know that virtual memory refers to all of the virtual memory that one program can access. So it's a little bit of a misuse of this term in this context, but hopefully this gives you a sense of how much memory is there on your system. Okay, what's virtual memory? So I'm going to recap a few important concepts from the previous lecture. So before we got into virtual memory, we talked about caches. So caches, unlike virtual memory, is completely controlled by the processor, meaning the decision to evict a cache block and when to replace it with a new cache block, all of those are made by the processor. Now we have been talking about main memory. We said main memory is not big enough to hold all of a program's data, and so we have to now start thinking about how to manage its space. If you run out of space, you have to spill into hard disk, which could be either a hard disk or a flash. And we said instead of delegating this role to the processor, we're going to delegate it to the operating system, because this transaction doesn't happen that often, so speed is not of importance here, meaning you're going to evict data and bring in new data so rarely that you don't need hardware support to do that. So that's the reason why we delegate the functionality of managing main memory space to the operating system. And the feature that operating system provides to manage the space is called the virtual memory. Now, virtual memory solves several problems. One big problem it solves, of course, is the capacity problem, meaning if a program's space exceeds that of what is available on main memory, you would spill to the disk. So virtual memory feature of the operating system manages the space on main memory and allocates it to different programs that are running on a system. So in addition to managing space, which is much like how we managed space in the case of caches, virtual memory also provides a couple of security features. One important feature is isolation, which means if many programs are running on a system, which is very common, I showed you in the previous lecture that I could have as many as 200 or more processes running on my simple desktop computer. You don't want those unrelated programs from accidentally accessing each other's data or maliciously access each other's data. Virtual memory solves this problem by allocating a different translation table to each one of the processes and making sure that two different processes can never access each other's data except when they explicitly want to share it. And we also talked about how this is possible by invoking the operating system calls to tell the operating system that I'm willingly sharing a piece of data. And this may be useful in cases where you have programs that have data that is useful for one or more programs. So that way you're able to reuse the same data in memory across many applications. There are other types of permissions that virtual memory maintains. For example, you may maintain read and write permissions to pages. Sometimes you may also want to maintain not executable bit, which is not shown on the slide, which again helps systems to enforce security policies. But the main thing that we deal with in this class is a capacity problem. And let me go through a slide that explains how the different pieces come together to manage the main memory space and disk space. The first thing to understand is that there are two addresses. One is a virtual address, which is the address that a load or a store instruction generates. The size of this address is defined by the ISA. In this example, I am assuming it to be 20 bits. Now, we also talked about how the virtual memory is divided into pages, much like how we divided memory into cache blocks before. For the purpose of main memory management, we are going to divide it into much larger blocks, typically 4 kilobytes in size. What that means is the lower order bits of the virtual address is now going to be treated as the page offset, meaning the last 12 bits are going to be used to index into a page and grab a data out of it. If you have a page size of 4 kilobytes, you need 12 bits from your virtual address. Now, this virtual address refers to a location in a program's virtual memory or virtual address space. So for a 20-bit ISA, which is the example I'm using, you would have 0 to 2 to the power of 20 minus 1 bytes. Now, if you divide this space by page size, you get the number of virtual pages in your program. So in this example, you have 256 virtual pages. Now, the very important concept to understand for virtual memory is that the operating system does not allocate all the virtual pages on a physical storage right away when you start the program. That will be too inefficient. Instead, what it does is it uses this concept of on-demand paging, where the program starts off by allocating a few important pages like the instruction page and the data segment page, but it doesn't allocate all of the space you need for heap and stack. And as the program executes, the operating system needs to be asked, please allocate me a page. And the operating system says, okay, here is the space for it. Okay. And so the main thing to understand is that when a program starts, not all of its virtual pages find space in the physical main memory or the physical hard disk. Some of them do. So in this example, I'm assuming that you have allocated 4 virtual pages, and I have highlighted that using 4 different colors. Now let's see how I may, or rather operating system may have allocated these 4 pages. So 3 of them are allocated in your physical memory. I'm assuming that my physical memory is only of size 16 kilobytes. And again, just like what I did for the virtual memory, I can divide the physical memory by the page size and figure out how many physical pages are there in my main memory. For this example, it turns out to be 4. And you will notice that 3 of them have been used by this program. So you have 1, 2, 3, and 1, 2, 3. So 3 of these pages have been allocated into the physical memory. And let's not worry about the page table yet. The 4th one is allocated on the disk. So the disk space is not infinite either. It is dependent on how much swap partition you have created on your computer. In this example, I'm assuming that an address like D100 refers to a file or a space, a location in your disk. All right, so this is our setup now. Now we have to ask the question, when I execute my program and when there is a load or a store instruction that generates a virtual address, how can I how can I translate this virtual address into this physical address? Again, the physical address refers to one of these addressees in the physical memory, right? So our goal is to translate a virtual address, which are these addressees, which is generated by a load or a store instruction, to a physical address which refers to one of these addressees, which refer to a physical page that is stored in main memory. Now you need to think about how big this physical address is. So the physical address is going to be as big as necessary to address the physical memory size. So in our example, we computed that given a physical memory of size 16 kilobytes, there are only 4 pages, and so the physical page number will have 0 to 3, which means you only need 2 bits. And so what you see here is I have 20 bits, 0 to actually 19, I think, if you have a 20-bit architecture. So this should be 19. So you have 0 to 19 bits, or total 20 bits. Of those 20 bits, 12 bits have been allocated for the page offset because the page size is 4 kilobytes. And that page offset does not change across the physical address and the virtual address. It's exactly the same because we are dealing with block of data of size that is of size page size, and so we are only thinking about which page is stored where. So the address translation only needs to worry about where is a given page located. So therefore we are not interested in the page offset when it comes to address translation. We are interested in translating a virtual page number 0 to 255 into a physical page number 0 to 3. Now this translation is done by, or explicitly kept track of, in this simple data structure called the page table data structure. So the page table is nothing but, in this example, a simple array indexed by the virtual page number, meaning for every virtual page number I have an entry in this page table, and that entry stores the physical page number, which I can then use to access my data. So if I zoom out here, you will see that virtual page number 0 has an entry in the page table, and it says that the virtual page 0 is stored in the physical page 1. And if I find the arrow here and I go here and I see that it is indeed true. So the yellow page is stored in the physical page number 1. Similarly, the green virtual page is stored at virtual address 1. I check the page table, and then I see that I can translate the virtual page number into the physical page number 2, and then go and find my green page. The pink page, again, there is an entry for it in the page table. It should have the value 3, and when I do the translation, I can then go and find out where the pink page is stored. And finally, some of these pages may not be allocated on the main memory. It may exist on the disk, and so those translations are also possible through the page table. So I will see that the virtual page 2, the blue page, is actually stored on the disk, and so you can find where on the disk the data is stored. In practice, when the operating system finds out that a page exists on the disk, it results in a page fault. A page fault is same as a cache miss, and the page fault handler would read the page out of the disk and bring it to the main memory, because to exploit temporal locality, you want to keep the page that you just recently accessed in your faster memory, which in this case is the main memory. And in order to do that, the operating system may have to pick one of these victims. So it may have to pick between 1, 2, and 3, evict one of these blocks out so that the new block can be brought in. All right, so now the page table structure itself needs to be stored somewhere. This whole structure here, this itself is a data structure, and it needs a place to be stored in memory. And so what the operating systems do is they reserve space in the physical memory for these page tables, and they store them over there. And so these page tables are typically pinned, meaning the operating system knows that page tables are super important structures that I would always need, so they are never evicted. So when you run out of space in the main memory, and when the operating system is looking to find a victim, it will evict one of the data pages but not the page table, and that's why it's called pinned. Okay. So to summarize, uh, the virtual memory is an operating system functionality that helps us manage the space in main memory, and at any given time a subset of the virtual pages are stored in the physical memory, and the addresses where and the page table maps the virtual addresses to the physical addresses where those virtual pages are currently stored. We talked about how when main memory is full, the operating system needs to find a victim page so that it can be evicted and make space for the new page. And like you may have guessed, just like in the case of the cache design, when we used LRU to approximate temporal locality, operating systems also use LRU-like policies to select a victim. But implementing a precise LRU policies is often very expensive because you have a lot more pages in main memory than cache blocks in cache. And so operating systems typically approximate the LRU policy. They don't keep track of a precise rank, LRU rank for all the pages. And one very simple way to approximate the LRU policy is as follows. You can maintain what is called as an access bit per page. It's just one bit. And what the operating system does is once in a while it goes and clears these bits, meaning it sets them to 0. And whenever a page is accessed, it would set that bit. So initially the accessed bit are all cleared, and as pages are accessed, this accessed bit is set. Now periodically the operating system comes and evicts pages to make space for new pages to be brought in. Now this could be done when you run out of space, and so what happens then is the operating system knows that any page without the bit set has not been accessed in the last period that just elapsed, right? So if you look at the timeline, so you start by saying clear all the accessed bits at time 0. Let's say this is time access. And then when the program accesses the pages, the OS will go and set the bit of those accessed pages. And let's say you run out of memory at time, let's say t dash. And then the operating system needs to make space. So what it does is it keeps all the pages with the accessed bit set and evicts all the pages with the not unaccessed, evicts all the unaccessed pages, right? Or instead of periodically doing it, you can also do it only when like you can set the accessed bit, and then suddenly let's say there is a page fault and now I need to make space, and so the operating system can go and pick a page with the accessed bit not set, and then periodically it can just clear all the accessed bits so that the whole process repeats. I also said that in the previous lecture, there are security features supported by the virtual memory. We talked about how it guarantees isolation. So what that means is in a typical computer, you're not just running one program at any given time, you're running a set of programs. So we looked at how my computer was running like 200 different types of processes. So when all these different types of processes are concurrently executing, in this example I have only 2 running, Chrome and Microsoft Word. Each of them have their own virtual space as defined by their ISA. So each of them have access to 2 to the power 64 different memory locations in theory. Now, those memory locations, the virtual memory locations, share the same physical address space. So all these virtual memory locations, I'm showing only a subset of all the virtual memory locations here, 0 to 10,000 or so, but in reality, the maximum size would be defined by the ISA. So in a 64-bit ISA, it could be 2 to the power 64. And similarly, Word has access to virtual address space that goes from 0 to 2 to the power 64, and you will see that the addresses obviously overlap with each other. And the way they are disambiguated is by allocating a page table, one per process. So Chrome has its own page table, Word has its own page table, and the address 0 gets translated to address 5000 for Chrome. The same address 0 gets translated to a different address for Word, because I have two different page tables that tell me where address 0 of Chrome is located and where address 0 of Word is located at the same instant. So this property of isolating the address space of Chrome and Word is implemented by the virtual machine through the management of these page tables. So that's the isolation property. Sometimes it is profitable for these programs to share data. One good example is sharing the library data. In that case, it's possible to share one physical page between same or different virtual addresses that exist in different processes. This doesn't have to be the same virtual address, it could be anything. But the big point here is that one process is able to share data with the other process so that you can save the physical memory space. If you didn't have sharing, then you'd have to store the same library code in two different places in the physical memory, and that is waste of space. So you could avoid that by collaborative sharing. And finally, virtual memory also allows us to keep track of special permissions. A couple of useful permissions to keep track of are read permissions, where, for example, your instruction pages, you may want to mark them to be read only, maybe because you're not expecting your program code to change when you're executing the program. You may also want to mark the data pages to be not execute, thereby disallowing the computer from interpreting your data as code, because that can become problematic, especially if you have other types of bugs like buffer overflows in your program, because that opens the door for attackers to overflow your data buffer and overwrite the data with their malicious instructions and then force the computer to execute their instructions. But by marking data as not execute, you're disallowing data to be interpreted as instructions. So if you look at the page table entry, and the page table entry refers to one entry in the page table. So I have, in this example that we talked about, we have 256 entries. Now I'm talking about what goes into each of these entries. The most important field in this page table entry is the physical page number. So in the example we talked about, that physical page number consisted of 2 bits, because I need to distinguish between 4 different physical pages. So I had to store 2 bits for the physical page number. But just like what we talked about now, there are other useful bits of information that can go into defining the property of the page. Like, for example, I want to say, is the page allocated or not? When I start the program, many of the pages in my virtual memory are not allocated, so they will be set to invalid. Is the page allocated on the main memory or the disk? That's useful for the operating system to know. And we just talked about how there are permission bits that are useful to be kept track of for different pages. So I may have access permission bits per page. I may also be interested in keeping track of whether the page has been modified by the program or not. Now we don't have write back caches in this example, but there are applications that would like to know whether a page has been modified or not. One good example would be a functionality called fork that operating system supports. So when an operating system needs to fork a process, typically it has to duplicate everything that is there in a process's address space, and the amount of data that needs to be duplicated is a lot. So an operating system uses an efficient policy called copy on write policy, where when you fork you don't really duplicate everything, but then you delay the duplication to a later point when a page gets modified, because only when a process that has been forked modifies a page, you need to have two copies, one for the child process and one for the parent process. Now those details you will go into much greater depth if you take 482, but a dirty page information is useful for those kinds of reasons. And obviously you probably want to have some metadata for your replacement policy, whatever that may be. We talked about an approximation of an LRU policy that just required 1 bit that told me whether I had accessed the page in the last period or not. So to summarize, a page table entry consists of many fields. The one field that we care about a lot in this course is the physical page number, which tells me which allows me to perform address translation. So here is a picture of how the address translation looks. So much of our discussion in this course would deal with the address translation, because I am interested in translating the virtual address created by the load or restore instruction and converting that into the physical address. So this example shows that I have the virtual address, which has two parts obviously. The page offset depends on how large your page is. So in this example, I'm assuming it's 4 kilobytes. So I have 3 hexadecimals worth of page offset, in other words, 12 bits. And the remaining part of your virtual address is your virtual page number. And then by looking into your page table, you can translate this virtual page number into the physical page number. And then simply by concatenating the physical page number with the page offset, you get your physical address. Now in this example, the sizes of virtual page number and the physical page number don't look that different, but keep in mind that virtual memory is much bigger than the physical memory. So typically a virtual page number will be much bigger than your physical page number. So let's go into a little bit more depth into how this translation works. I need to first locate where my page table is. So the operating system needs to know for a given process where in the physical memory that process's page table is stored. So the operating system internally maintains that base address, but when you're running this program, the operating system stores that base address in the special register called the page table register. It's a special register that stores the base address of the page table of a process. And so when you have a load or a store instruction that generates the virtual address, the operating system will use this contents to retrieve the base address of the page table, and then the index into this page table would be the virtual page number, because at the moment we are simply treating the page table to be a linear array indexed by the virtual page number. And as we just discussed, each page table entry contains a physical page number. In this example, I'm not showing the permission bits and all those other entities that go into a page table. I've simplified it to contain just the valid invalid bit and the physical page number. And so you retrieve the physical page number and then you concatenate that with the page offset. What you get is a physical